Hi Mr. Lee, my name is Lydia and I am trying to find out as much as I can about Layout IQ. I need to use it on a class project for my facility layout planning class at my university. Can you introduce Layout IQ in a nutshell?
Hi Lydia. It's nice to see you. Winston Churchill once said, "We shape our buildings, and afterwards, our buildings shape us." End quote. Nothing impacts the productivity and profitability of an organization more than the waste caused by the inefficient organization of facilities and workspaces. I started my career as a simulation modeling and optimization engineer working as a consultant in manufacturing, healthcare, and warehousing. After working on many simulation projects with poorly designed layouts, I realized that I needed a better tool to quickly create optimized layouts for my simulation models. At the time, I was using AutoCAD with an add-on that performed basic flow diagramming. I needed something that was dynamic and more robust than what a CAD solution offered, and I wanted a lightweight program that didn't require a third-party CAD system to license and learn. In a nutshell, I created Layout IQ because I needed an easier, simpler, and faster way to create better layouts in my consulting practice. As I began using Layout IQ on commercial projects, and presented the results to clients and at conferences, it became clear that Layout IQ was the perfect teaching aid for educators and students at the university level.
That makes sense to me. Now that I know why you created it, I'd like to know why it is different. What are some of the features that make Layout IQ exceptional in the classroom and indispensable in the design studio?
Thanks for asking that question. It is a good one. To demonstrate these features, I am going to open a project of a hospital that was building a new nursing tower. The project included creating a baseline model of the existing tower, to be used to compare with the new tower design. Let's jump over to the software now.
Okay, sounds great.
First, as I am opening the model, I want to point out that Layout IQ is a standalone software. It doesn't require a CAD system like AutoCAD to work. Because of that, the program is much smaller and optimized for speed and simplicity. Students don't have to license and learn a third-party CAD system to use the software, which is a huge plus. Second, Layout IQ imports CAD drawings in standard graphical formats so you can start the model with an existing layout if you have one. In the current model I have imported the existing CAD layout, as you can see from the layout. Since the building already exists, the CAD drawing makes it easier to illustrate the flow accurately through an existing layout. Third, Layout IQ calculates Euclidean travel distance, which is a straight-line path between locations. Euclid was the Greek mathematician who postulated that the shortest distance between 2 points is a straight line. It is always best to create and optimize a layout in the Euclidean diagram first, and then create and optimize the aisle plan in the actual path diagram. Fourth, Layout IQ calculates the actual path travel distance. The software also gives the user control over the paths people and material take instead of forcing flow down the shortest path. This provides a more accurate model of flow. I will demonstrate the process of creating the actual paths later in the tutorial. Fifth, Layout IQ also calculates the aisle effectiveness metric. This is calculated by dividing the Euclidean travel distance by the actual travel distance. This value tells us how effective the aisle plan is at moving material and resources through the layout. For space syntax users, aisle effectiveness can be used to represent proximity and visual control. It also measures the potential for improvement of the aisle plan. Sixth, the thickness and color of the flow lines represent the intensity of flow down each path. Wider lines represent higher traffic. There are 4 colors that represent flow. Red represents the top 25% of flow. Then yellow represents from 75% to 50%. Then green represents from 50% to 25%. And blue represents the bottom 25% or lowest intensity flow lines. Because red and yellow lines represent higher intensity flow, we know intuitively that they need to be as short as possible. Notice in this real-life example that there is a high intensity of flow between the patient rooms and the nursing station. In the new design, one of the goals will be to shorten the length of these flow lines, which will significantly reduce nurse travel. Next, let's take a look at the model of the new tower. This model was used to optimize the physical layout and aisle plan of the new design. Notice that the thick red lines are much shorter than they were in the existing unit design. The reason is because workstations were added in the hallway outside each patient room, which moved most of the work nurses do in the nursing station closer to the bedside. 7th. Layout IQ has a dynamic engine that calculates the travel distance as you are making changes to the layout. It makes it a lot easier to get to an optimal layout when you can see the impact of the changes you are making dynamically. To illustrate this point, in the new tower model, notice that there are long thick yellow lines between each patient room and the narcotics dispenser. To find an optimal location for the narcotics dispenser, I can move the narcotics dispenser location around the layout until I find the shortest distance. As I make these changes, the software calculates travel distance on the fly. Notice how I can move the arrow keys 1 pixel at a time until I find the sweet spot.
I can see that you are moving the location 1 pixel at a time, and that the dynamic engine is recalculating the travel distance every time you move it. If I understand you correctly, you are looking for the location that has the smallest travel distance, and that is the sweet spot. It looks like you found it.
In review, the thickness and color of the lines help me find which locations to move to get the biggest reductions in travel distance. Then the dynamic engine helps me to quickly find the best spot for that location as I am moving it around by minimizing the distance traveled.
If you don't mind me interrupting here, that sounds amazing. You mentioned that the software has a dynamic engine. That sounds really complicated. Can you tell us more about it?
Sure. There are so many different types of changes that a user can make, and it is very difficult for the software to know how to handle those changes. This is why it has never been done before Layout IQ. To handle the complexity, I developed a brain in the software that contains all the methods required to be able to recalculate travel distance and aisle effectiveness when changes are made. It is extremely complicated. I refer to this as a dynamic engine because it performs those algorithms thousands of times as the user is building the model.
That's amazing. It sounds like artificial intelligence applied to layout planning.
That is exactly what it is. Continuing on to feature 8. Layout IQ has an experimentation feature that allows users to create and score multiple layout alternatives and compare them to each other quickly and easily to find the best one. I will demonstrate this feature on a project whose goal was to determine the best way to store supplies on a nursing unit. Notice I have already created 2 scenarios in this project. Let's look at the central supply experiment first. Notice that this layout has a single central supply location in the center of the nursing unit. In the central supply experiment, nurses will walk 1,828,151 feet in a month for supplies in this layout. That seems like a lot. Next, let's look at the distributed supply experiment. Notice that this scenario has 4 supply locations spread out in the unit. Notice the significant improvement in actual travel distance. 677,170 feet walked in the distributed supply experiment compared to 1,828,151 feet in the central supply scenario. That is a 63% reduction in nurse walking. 9th, the software produces detailed reports in Excel, so users can do additional analysis outside of the software. Users can also run a report that compares the experiments side by side. This report ranks the experiments from best to worst based on actual travel distance and aisle effectiveness. This allows the user to rapidly test as many design scenarios as needed and to quickly find the best scenario. Isn't that cool?
That is really cool, but I have a question. What does the data look like and where does a user get it?
There are 3 data templates that Layout IQ supports for calculating flow in a layout. The method you choose to model flow in your layout depends on the data formats you have. The simplest modeling method is called from-to trips. It is used if you have a simple count of how many trips are made between locations. This method is best explained by a project I did at a hospital recently. In a conference call with the hospital, they explained that the nursing team felt that the current method of centrally locating supplies on a nursing unit was causing nurses to walk excessively, and taking them away from their patients. They wanted to switch to a new process of distributing supplies in the unit, closer to the bedside. However, they couldn't get the materials department, whose responsibility was to restock those supply locations, to buy into their plan. So we asked them, how many times does a nurse walk from a patient room to a supply room and back again? After a few minutes they agreed that nurses made this trip on behalf of each patient approximately 10 times per day, or 300 times per month. Within less than an hour, we were able to build both the central supply experiment and the distributed supply experiment. Since the model is already open, let's jump straight to the central supply experiment and look at the data. In the central supply model you can see that we have defined flow between each patient room and the supply room 300 times. And 300 times from the supply room back to each patient room. Now let's look at the layout. Notice the thickness and color of the lines in the diagram are the same. It is because all the flow lines represent 300 trips from each patient room to the supply room and back again. Now let's look at the distributed supply model. In the distributed supply experiment we added 3 new supply locations and distributed the flow to the closest supply location. Notice the number of trips is exactly the same, they are just going to different locations. Now let's look at the layout. Notice the thickness and color of the lines in the diagram are the same, but the flow is going to new locations. The models showed that the central supply model caused nurses on this unit to walk in excess of 2,615 miles per year more than the distributed model. It is the equivalent of nurses walking from Los Angeles, California to Boston, Massachusetts. As you can imagine, the distributed supply plan was immediately approved.
It is incredible that they could eliminate that much walking on one nursing unit in a year. How many nursing units did the hospital have, and did they consider distributing supplies on all of their units?
They had 10 identical units. They estimated that they would eliminate nurses walking in excess of 26,000 miles per year hospital-wide by distributing supplies on their units.
Wow, that is more than the circumference of the Earth. I guess that eliminating wasteful walking is a great way to get nurses to spend more time with patients, isn't it?
It certainly is. The second data template that I would like to show you is called process routing. This data template is typically used for manufacturing. It can also be used in many other industries. Process routing is the most detailed method in Layout IQ. To demonstrate process routing, I am going to open a model of a factory that produces power tools. In the process routing method, products are objects that have their own routing and they can be selected in the flow diagram. In the process routing method, you enter a production volume for each product. Many manufacturing companies store their process routing data in a format that can be imported directly into Layout IQ. Importing the data is a lot faster than typing it in the data editor. You can also manually enter the data in the form. Layout IQ is able to determine the path, and calculate the number of trips made between locations as the product moves through its process routing. The formula is product volume times flow factor divided by unit load. This is a real model of a factory that produces power tools. The factory produces 19 different power tools, has 2,712 routing lines, and ships 194,592 end items per month. When you have a factory that is this large, it is advisable to maintain a Layout IQ model so that when things change, such as production volumes and model mixes, you can quickly evaluate the impact of those changes on the layout. This allows the manufacturer to adjust the layout to stay as efficient as possible. In the process routing method, you can select any combination of products and view their flow through the layout. Notice how the travel distance and aisle effectiveness changes dynamically as I select each product. Users can also import data from an RTLS system. RTLS is real-time locating of products, people, patients, and resources. These systems track objects as they move through a workspace, and produce a database that can be formatted in the process routing table format, and imported into Layout IQ. This next model is an example of an emergency department that used an RTLS system. The RTLS system used an employee badge that had a built-in transmitter. As employees moved around the ED, the system knew where they were because their tags transmit a ping. Detectors in every room were able to receive the ping, which told the system that the employee is in that room. When using the process routing method to model RTLS data, the product name becomes the badge name. The process routing data is a record of everywhere the employee traveled and every trip the employee made. Let's look at the layout now. The products window contains the list of badge names, which were the nurses working in the ED. I can select any nurse and view their Euclidean travel distance. I can also view their actual travel distance and aisle effectiveness, and I can select any combination of nurses to get a comprehensive view of the flow through the layout.
It is so convenient to be able to drill down on a single product or any combination of products. I can see now how powerful the dynamic engine is. I can't wait to see the subjective method.
The subjective method is based on a method which has been taught in industrial engineering textbooks for many decades called systematic layout planning or SLP. This method uses the opinions of people using the workspace, and the opinions of other key stakeholders. Each person providing an opinion ranks the importance of the location-to-location relationships on a scale of 6 levels of importance. They are A. Absolutely important, E. Especially important, I. Important, O. Ordinary importance, U. Unimportant, X. Closeness undesirable. Users can give a higher weighting to those opinions that have more expertise. For example, the opinion of an RN might be more important in the design of a patient room than the opinion of an assistant. To demonstrate, I will open a model of a patient room. The purpose of this model is to determine whether it is better to locate the head wall on the near wall or on the far wall. We are looking at the scenario with the head wall on the far wall first. For this model, we have interviewed 2 people who use the workspace. We can give a person more influence by applying a higher weight to them. For example, an RN's opinion may have more influence than an unlicensed assistant. We can also create opinions for different products that move through the workspace. In the case of a patient room, there are high acuity patients and low acuity patients. We can also add weights to these. In this model, we have given more influence to high acuity patients. A person's location-to-location rankings are created in the Opinions tab. Notice in this interface we can create as many opinions as are needed. In this model, each stakeholder has ranked the importance of each location to every other location using the A, E, I, O, U, X scale. Let's look at the layout now. The thickness of the flow lines are calculated depending on the importance of the location-to-location relationships. A is 5, E is 4, I is 3, O is 2, U is 1, and X is 0. Following this method, we can improve the layout by reducing the length of the red lines first, then the yellow lines second, then the green lines in that order. That will ensure that the highest importance location-to-location relationships are prioritized. The primary goal of the model is to find the layout with the smallest actual score.
I understand now. The subjective model doesn't model actual flow. Instead, it is relying on the perceptions of the users of the workspace and the stakeholders. I wonder how closely a model created by the subjective method would compare to a model that uses actual flow data. Have you ever used the from to trips or process routing methods and subjective method on the same project? I would love to know how they compare.
We have done many projects using actual flow data and simultaneously created a subjective model of the workspace. If the question is, how accurately does the subjective model compare to actual flow? The answer is typically not very closely. This is why we prefer to use the from to trips or process routing methods as the primary methods to layout creation. We use the subjective method only when there is no flow data or if we have a client that asks for it.
That was fascinating. Do we have the time for you to demonstrate how a model is built, and how to create the actual flow diagram?
Definitely, let's do it. In reviewing the patient room model, I am noticing that there is some significant walking to the far side of the bed. I am curious about what would happen if we moved the cardiac monitor to the near side of the bed. For this demonstration, we will create another scenario of this model. To begin the new model, we are going to create a new experiment and copy the current experiment. This brings all of the people, products, opinions, and locations into the new model. This ensures that the difference in the scores of the two models is only the result of moving the cardiac monitor. Because moving the cardiac monitor will affect all of the actual paths, I need to start this model by recreating the actual path. Therefore, I am going to delete the existing path network, then move the cardiac monitor. Before I move the cardiac monitor, I am going to reduce the relative thickness of the flow lines so I can see and work with the flow lines more easily. I am also going to remove the labels for now, which will make it easier to work with flow lines. Now I am going to recreate the actual path. To do this, I will select the actual path setting. In this mode, I can grab a line and pull it down the path I want it to go. When I release the mouse, a node on the path is created. If I want two lines to go down the same path, I can merge them together by dropping one node on top of the other. The system merges the nodes, recalculates the thickness and color of the flow lines, and recalculates the score and aisle effectiveness dynamically. Watch as I quickly create the actual path network. In the new experiment, the subjective score is 7,717 and an aisle effectiveness of 76%. Now let's look at the far wall experiment. Compared to the far wall experiment where the subjective score is 9,215 and an aisle effectiveness of 70%. That represents a 16% improvement in the overall score and a 6% improvement in aisle effectiveness just by moving the cardiac monitor to the near side of the bed. This is a good example of how one change can make a significant improvement towards eliminating waste in a layout. That completes our introduction to Layout IQ. I hope you took great notes.
I did take notes, but I'd like to make sure I got all of the important stuff down. Do you mind if I review them quickly?
Sure.
We started with the 9 features that make Layout IQ so effective for designing and analyzing a layout. Then we learned about the 3 data types and modeling methods. Starting with the 9 features that make Layout IQ unique. They are: Number 1. Layout IQ is a standalone program, which makes it light and fast. You don't need a third-party CAD system, such as AutoCAD, to use the software. Most industrial or manufacturing engineers aren't regular CAD users and don't have access to a CAD license. This is why Layout IQ is the perfect fit for them. They don't have to license and learn a CAD system to do layout planning. Number 2. Layout IQ can import third-party CAD drawings if one is available. This allows the analyst to benefit from CAD without having to be a CAD user. Number 3. Layout IQ calculates the Euclidean travel distance, which is the shortest possible distance between 2 points. Number 4. Layout IQ calculates the actual path travel distance, which includes travel down aisles and through doors. Number 5. Layout IQ automatically calculates aisle effectiveness, which tells us how efficient the aisle plan is. This is an important feature for space syntax users. Aisle effectiveness is equal to Euclidean travel distance divided by actual travel distance. Number 6. The thickness and color of the flow lines represent the intensity of flow down each path. The widest red lines represent the highest traffic, then yellow, green, and blue in that order. Number 7. Layout IQ has a dynamic engine that calculates travel distance and aisle effectiveness on the fly as you are making the changes. Number 8. Layout IQ includes the ability to create and analyze as many layout experiments as needed to complete the project. Number 9. Layout IQ provides a comprehensive report that can be used for further analysis, and a report to compare and rank experiments. Next, the 3 data types and modeling methods in Layout IQ included the following. First, the from 2 trips method, which is the easiest modeling method. Second, the process routing method, which is the most detailed method. Process routing usually requires the organization to have flow data in a format that can be imported into the software. This can be from an ERP system or from a real-time locating system. Third, the subjective method, which is also referred to as systematic layout planning, or SLP. This method relies on the opinions of the stakeholders. Well, how did I do?
You did a great job, Lydia, 100%.
I have learned so much today about how to create a better layout, and I have a whole new appreciation for Layout IQ. The dynamic engine adds so much value to the process. Thank you for taking the time to introduce me to Layout IQ. If anyone watching this video is interested in learning more, how do they contact you?
They can contact me by email at nlee@rapidmodeling.com, or call 513-624-6629. Thanks for letting me show you Layout IQ. Goodbye for now.